I'll be talking about distfreereg, which is an R package that I wrote on CRAN. That, as he said, implements a distribution-free goodness of fit testing procedure for parametric regression models. When we use a model like this, in particular for inference, we rely on the assumptions of the models being sufficiently well met. For example, if we have a linear model with a misspecified mean, the resulting p-values can be very misleading. And this is what goodness of fit testing allows us to verify. Sometimes graphical methods can be used, but often we want a formal test. The model form that we'll be considering is very general. Y equals f of x theta plus epsilon. Epsilon is a mean zero error term. And the particular assumption that we want to test is the correctness of the mean function specification. Probably the most important assumption when working with a parametric regression model. Specifically, the null hypothesis that we'll be testing is that for some d-dimensional parameter vector theta, the expected value of y given x is equal to f of x theta. And the alternative hypothesis is the negation. Given how fundamental this is to using models, it's reasonable to ask, do we need an R package for this? Are there not already R packages that do this for us? I was only able to find 6 other packages on CRAN that focus on goodness of fit regression testing. Most are not being actively maintained, and some of those are not fully developed. 3 focus on single kinds of models, so for example, they only apply to linear models. 1 only handles models with a single covariate, and the remaining 2 only models among LM, GLM, and NLS objects. In addition, they're all fairly inefficient for testing, or for investigating rather, certain test properties. So power, for example, or more generally, anything that will require that you run the test thousands or tens of thousands of times. My answer, therefore, to the original question is yes, we need an R package that is widely applicable, efficient, and easy to use. And that's my intention for distfreereg. The procedure that I implemented was introduced by Estate Khmaladze in 2021 and extended slightly by Sarah Algieri and others shortly thereafter. It does apply to a wide variety of mean functions, makes minimal assumptions about the joint distribution of the errors, hence the distribution-free aspect of the test. In particular, they don't need to be IID, and they don't need to be normal. They can be, but they don't need to be. So we could test an LM object, a GLM object. And as far as I'm aware, there is no other implementation of this algorithm in any software, either R or otherwise. The theory behind the procedure is beyond the scope of a single talk, but I do want to give you at least a very brief outline of the algorithm to give you some sense of what's going on under the hood. Step 1, not surprisingly, estimate theta. So we use the data to get theta hat, and we use that to construct a vector of sphered residuals. These are just the raw residuals left multiplied by the inverse square root of sigma, the covariance matrix of the errors. In step 2, we'll apply Khmaladze's transformation. This is described in that 2021 paper. It's really the heart of the technique. We apply this transformation to epsilon hat to get a vector of transformed residuals, and then we form its empirical partial sum process V sub n. Because of the transformation, the way this transformation works, V sub n's asymptotic behavior under the null hypothesis is independent of both the mean function that we're testing and the error distribution. In fact, it's dependent only on the sample size n and the dimension d of the parameter space. Once we have V sub n, we calculate test statistics on it. It's our primary object for testing. We can choose what test statistics we want to use, so we're actually implementing a procedure that can conduct multiple tests simultaneously. And finally, we'll simulate the null hypothesis distribution of these statistics and use what we have in step 3 and step 4 to approximate p-values. Because of the independence mentioned in step 2, this simulation is remarkably straightforward to implement and usually very quick as well. So let's look at an example. The most general kind of example that the package can handle entirely within R is when the mean function we're testing is specified by a function. In other words, an R object of class function. So all of this is just set up. We're going to generate data from a nonlinear model with the form given at the top of the slide, and we'll use a non-diagonal covariance matrix for the errors. And now we'll define the function that we want to test. I'll suggestively call it wrong mean. It's equivalent to the true mean function from the previous slide that was used to generate the data, except that x2 term is now linear, where in true mean it was quadratic. To conduct the test, or conduct the procedure, we call the distfreereg function. And we supply it with the mean function that we want to test, which here is wrong mean, the data, y and x, a vector of starting values for parameter estimation, and the covariance structure. The default printout shows a little bit of summary information at the top, including parameter estimates, and then we have a table of observed statistics. By default, a Kolmogorov-Smirnov and a Kramer-von Mises-like statistic are both calculated, and the p-values are shown in the third column. Note that both p-values are fairly small, indicating that we have correctly rejected the null hypothesis using both tests. Also note that both p-values are obtained using Monte Carlo simulation, and so they have associated Monte Carlo standard errors, which it is wise to report. Those are shown in the fourth column. And here the key is that these are about an order of magnitude smaller than the p-values themselves, so we are satisfied with the precision of our p-value estimates, especially given their relationship to reasonable thresholds. There are additional methods for various model classes, LM, GLM, LMER mod, and NLS. So if you have a model, any of these models already created, to implement this procedure, all you need to do is supply the model itself as the value of the test mean argument in distfreereg, and the function takes care of everything else. So this is just example. There's no object M that I've created. But that's all you need to do. Plotting, I think, is an important part of any analysis, and there are various options for plotting a distfreereg object. The default behavior is to show an estimated density curve of the test statistic under the null hypothesis. And there's some default annotation and a 95% simultaneous confidence band is constructed and displayed around the density curve. So I just want to emphasize it is not a pointwise confidence band, it's a simultaneous confidence band, constructed using a technique that will be described in an upcoming paper. There are various options for using the function, a few notable ones. There is a stat argument that, as I've alluded to, allows you to specify your own statistic or statistics. You're not stuck with KS and CVM. If you're using the function method, which is what we used earlier, you're allowed a lot of flexibility in how you specify the covariance structure of the errors. If you're using a model object, you don't need to do that. It's extracted from the object automatically. There's an ordering argument that determines how the observations are ordered when you're constructing the empirical partial sum process. And there's a control argument, like a lot of R functions have. It's analogous to that. I want to say one more thing before moving on to the second of the two main functions in the package, which is called compare. And it's going to be related to that, which is efficient updating. When possible, when updating the distfreereg object using the update function, the elements of the object are used instead of being recalculated. So for example, if you want to update the function with a new y vector, a new outcome vector, but everything else is the same, no part of the procedure requires that you rerun the simulation for the null hypothesis distributions of the test statistics. Those are dependent only on n and D, and neither of those change if all you change is Y. So this saves a little bit of time if you're updating once, which can still be important. It saves a great deal of time if you're updating 1,000 times or 10,000 times, as we'll talk about next. So the second of the two main functions is called compare, and I want to talk about this first by way of sample size requirements. Khmaladze's method relies on asymptotic results, and so it's a very reasonable question to ask in any particular application whether the sample size is adequate for the simulated null hypothesis distributions of the statistics to approximate the actual distributions well enough. If we have a distfreereg object in hand, such as DFR from before, we can use the asymptotics function to do this. When we supply DFR to asymptotics, it takes the test mean function from that object, uses it to generate a new y vector, and then updates DFR with that new y vector. So we get another test statistic. I'll call it observed, even though it's simulated. So we get another observed statistic. And it does this again and again and again, by default 1,000 times. So we end up with a vector of 1,000 of these new test statistics. But we already have our Monte Carlo simulated statistics. If the sample size is adequate, the distributions of these two sets of numbers should be approximately the same. One way to look at this is to plot. So the plot method, the default behavior for the plot method for this class of object is to show estimated cumulative distribution functions for both the observed and simulated statistics. And here we see they overlap quite nicely, indicating that a sample size of 200, which is what we're using in this simulation, is adequate. There is also a rejection function that allows us to extract numeric information from the simulation, in particular the rejection rates. And here these are type 1 error rates, fairly close to the nominal rate when we're using 0.05. Associated Monte Carlo standard error is also shown. Now, asymptotics is actually a wrapper for this much more general function called compare. And among other things, compare allows you to use one function to generate y, and another function to be the one that you send to distfreereg for testing. And so this allows you, among other things, to investigate the power of the test against this particular alternative. So for example, if we want to estimate the power of this test, really two tests, when we're generating data with true mean and testing wrong mean, which is the situation we were in when we made DFR, then we can update CDFR, that call to update we'll call compare, with true mean as the data generating function, and we'll also supply it with the true parameter vector that we used in that simulation. And the plot now shows two very distinct CDFs, very high power against this alternative. The rejection function can be used here. Now these rejection rates are power, 97, 98%, around there at the 0.05 level. And rejection allows you to specify other significance levels, and you can focus on a single statistic if you'd like. I do want to point out that distfreereg, the procedure is distribution free in that we're making minimal assumptions about the distribution of the errors. When we're running these simulations, we're generating data, and so we are making distributional assumptions. If you're using model objects behind all of this, it's using simulate, so whatever the behavior is, LM has a method, GLM, these things work with simulate, as does LMER mod. In this case, when we're using a function object, right, object of class function, it generates using multivariate normal. There is an argument for compare, though, that allows you to specify any distribution function that you want, so you're not locked in to this assumption. You do have to make an assumption, but in these simulations, you get to choose what it is. As I said at the beginning, the package is available on CRAN. You can go directly to this URL. You can just search for distfreereg as well. It will probably be the only thing that comes up. My email is available on the CRAN page, If you have any questions or comments, feel free to get in touch. I would love to hear anything you have to say about it. And thank you.